of asymptotic approximations of integration, method of stationary phase and steepest descents. So I'm just going to jump right into Laplace method for stationary maxima today. On Friday, we talked about Watson's lemma, which is a specific case that allows us to handle Laplace type integrals. But in general, we may have some integral of the following form, where we have some asymptotically large parameter x, and the variable of integration here, we have some non-trivial function phi of t in the exponential here. And as suggested by the title stationary maxima, we have some max of that particular function. And we're going to consider three general cases, okay? So one of those is that phi of t has a max at some value c, where c is between the limits of integration. And so in particular, this means that we can say that phi prime of c is equal to 0, and phi prime prime of c is less than or equal to 0, just the conditions for that to be a maximum. So if we look at this, if we have our limits of integration here and some c value, there's our max there. And I of x in this case can be split up into sort of the region right around this max, and then the two subdomains outside of it. Because the primary contribution, if x is large, is going to be from this region right here, okay? So I can write I of x as the integral from a to c minus some small parameter epsilon c minus epsilon c plus epsilon plus integral from c plus epsilon up to b f of t e to the x phi of t dt, again as x goes to positive infinity, okay? And then we'll talk about how to deal with this integral then, but a lot of times you can then bound out these contributions here and essentially say that they're going to be of next order, and that the leading order contribution is going to be from here and from some expansion about this maximum, okay? So I'm just writing those cases for now. We'll go through the details in a little bit. Phi of t could also have a max at a. So in that case, we would have phi a, b, and our function, looks something like this. There's our max here. And in that case, I of x would just be given to leading order by the integral from a to a plus epsilon, just some region around that left boundary, e to the x phi of t dt. And here, the only condition we need is that phi prime of a is less than or equal to 0. Or that's the only thing that we can say for sure, that we have some global maximum there on our domain a to b. Okay. The mirror image of this is if we have a right boundary max, okay? And phi looks something like this. We have some max here. And in that case, to leading order, the integral from b minus epsilon up to b f of t e to the x phi of t dt phi prime of b is less than or equal to, greater than or equal to 0. We approach from the right, and this is valid for x is large here, okay? So we see that this for Laplace's method here, as for other methods of asymptotic integral approximation, if you have a primary contribution to your integral in some subregion, okay, then you can either cut that off or essentially rewrite the integral so that you sort of retain only the part. The main part that's left unchanged is going to be the region of the integral around A. And in fact, if you have exponential decay, you can often just say, well, alternatively, I could extend this integral out to negative infinity and positive infinity if that integral is easier to compute than the other ones, and the contributions that you'll get by adding on more domain are going to be of smaller order than your leading order contribution here from the maximum. Okay, so what do you do about phi in this case? Because the idea is if you have some nonlinear function up here, you may not be able to explicitly calculate this integral. That's why we're resorting to asymptotics. Okay, the idea is that if we expand phi of t and f of t in some neighborhood of our critical point, okay, then we can assume that to leading order, f of t is just approximately equal to its value at that critical point, right? In each of these three cases, okay? It's either equal to f of a if you have the critical point at a, f of b if you have the critical point of b, or f of c if you have the critical point at c, okay? And t, as t goes to a, b, and c, okay? And as long as f is not just 0 there, so we actually experience whatever variation there is in phi of t around that point, okay? So let's unpack what we do in case 1, right? That would be this case here where we would just take f of c. In case 1, right, we already know that phi prime equals 0 at c. So we can write that a Taylor series expansion of phi about c is now just going to have this 0 and then this second order term here, okay, as t goes to c, okay, to leading order. All right. Now, you may have some, quartic type maximum, and so this part vanishes too. So whatever the first order of derivative is that's non-zero, that would be the additional term that you tack on in this case. So if phi prime prime of c equals 0, then phi of t has a two-term expansion that's just given by phi of c plus 1 over p factorial, the pth derivative of phi at c, and t minus c to the p as t goes to c, okay, for p greater than or equal to 2. And because it's a maximum, then p should be even then, okay? Now, if we assume that we have some non-zero value of our second derivative here, okay, then phi p of c, let's say this is less than 0, right? This ensures our maximum. How does this integral now look in case 1? Okay, well, to leading order, because the primary contribution is about this maximum, the integral is going to be from c minus epsilon to c plus epsilon, e to the x phi of c plus x over 2 phi prime prime of c t minus c squared dt. And now you can kind of see what we've done here, right? Is we have just some exponential times some scaling that doesn't involve t that we could pull out. And we have some exponential involving our argument, the square of our variable of integration here. Okay, so it's going to be a Gaussian integral. Okay, now you can use error functions and the like to compute this integral, but because this is going to fall off significantly, because this is going to be negative, right? We have some Gaussian type function that's going to drop off very abruptly around t equals c, right? So here's c, okay, here's t, and then here's e to the minus x over 2, absolute value of phi prime prime of c, right? Because remember, phi prime prime is negative, okay? T minus c squared, right? So this falls off very abruptly. So if we integrate this, really all that matters is just the region around here, okay? So the fact that I've truncated things out to A and B, okay, it's not going to matter that much if I extend that domain of integration out to minus infinity and positive infinity. And the advantage of that then is that I can use a much simpler formula in order to perform the integration of that Gaussian function from minus infinity to infinity. Okay, so the idea now is that I'm going to rewrite I of x, okay, to leading order as f of c. I can pull out f of c, e to the x phi of c. I can pull that out. Integral from c to the minus epsilon c minus epsilon c plus epsilon x over 2 phi prime prime of c t minus c squared dt. Okay, and then this is my next step now, is to say, well, f of c e to the x phi of c, okay, integral now from minus infinity to infinity, e to the x over 2 phi prime prime of c t minus c squared dt. Okay, so this is an integral I don't have a problem doing. I just use my sort of standard formula for a Gaussian integral from minus infinity to infinity. Okay, so that's case 1. That's the idea here to leading order. Okay, now we'll talk that there are ways to move beyond this leading order term. If you want to jump to it, it's in Bender and Orszag has it in their chapter on Laplace integrals. But the idea essentially is that you go out to more terms of this integral, and you use those to provide these additional corrections.
If f of c was 0, as we assumed it wasn't, would you just go to the next term in the expansion for f?
Right. Yeah. So yeah. So the idea is that instead of just Taylor expanding the whole integrand, right, you're sort of separately just Taylor expanding f and phi in this case. Okay. But by continuing those expansions, you should be able to pick up more terms in these integrals. Okay. All right. So that's case 1. Case 2 and 3 are quite similar to one another. It's just that you're stuck against the boundary now. Okay, so now in this case, let's say I of x. Let's take case 1, right? Through a similar procedure, we're going to get to an integral that looks like this: e to the x phi prime of a. Okay, but now instead of our expansion going out to phi prime prime, right? Because the maximum, right, could happen because you have a decreasing function there. Okay, this could be non-zero, phi prime of a. If it's 0, you just go out to phi prime prime of a, right? And if that's 0, you go out to phi prime 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 of a. Okay. Through the same logic as case 1, right, we can rewrite this integral as f of a e to the x phi of a, integral from a to infinity, e to the x phi prime of a, t minus a dt. Okay. And right, if phi prime of a equals 0, okay, go to phi prime of a, etc. Okay, if f of a equals 0, go to f prime of a, etc. Okay. And in case 3, you have something analogous. You're just on the right boundary instead of the left boundary of the domain of integration. Okay. So that's the idea how to set up these leading order integrals. Okay. Any questions about the logic behind these?
I was wondering, what if A and B have the same value, but like say there's a dip in the middle, like we had some periodic phi or something, or just we need to do both ends in, but not the middle piece.
Yeah, then you do both. So if they contribute in the exact same way, then you can essentially split the integral up, right? Do something like this. You could chop here and you chop here, and then you do your extension of this one out to positive infinity, and you do your extension of this one out to negative infinity, and you say the integral is the sum of those two things. Now, what you might find is then that maybe the integral on the left, from the left part, is the dominant one, and then your leading order would just be given by the left one, right? Because it could have to do, like, if this had the exact same value of this, right? But if this one sort of decayed slower than the one on the right, or something like that. Okay. So you can always kind of include more terms and then truncate back if you realize you have these additional terms that are of lower asymptotic order.
Makes sense. Thank you.
Okay. Yeah, good. All right. Let's return to case 1 now and look a bit closer. These Laplace integrals. And just to clean things up a bit, let's change variables to s equals minus x phi prime prime of c divided by 2 to the 1/2 t minus c. Okay. Well, then our differential now has this 2 square root of 2 over minus x phi prime prime of c ds. That's going to give us a simpler function to integrate. Okay, so now we have this term becomes a prefactor to our integral. Okay, and our integral now is just e to the minus s squared ds. Okay. Now, yeah, I'm sure you remember this trick from Calc 2 or Calc 3, right? Where you take the product of two integrals like this. You can use polar integration, right? And you can show that the integral from minus infinity up to infinity of e to the minus s squared ds is equal to the square root of pi. Okay, so at the end of the day, what we get then, and this is still for a fairly general formula, is f of c is involved in our leading order term. E to the x phi of c is involved in our leading order term. Okay, minus x to square root of 2 pi over minus x phi prime prime of c is in our leading order term, as x goes to infinity in the case where p equals 2. Okay, so even though we chop to some order epsilon version around, right? Remember, we expanded back out, so epsilon doesn't enter into it, right? Only the value of f at your maximum enters into it, assuming that it's non-zero, right? And then only phi at c and phi prime prime at c enters into it. And then, of course, your x here appears both in the exponential and in this denominator here. Okay, this square root denominator here. Okay. So I'll make a remark at this point. So 2 additional terms for f of t and phi of t expansions are needed for a consistent expansion to second order. Okay, so if you're going out to second order, you want to include f prime and f prime prime in your expansion, and potentially for phi, then you would want to include going out to phi prime prime and then the fourth derivative of phi in that case. Okay. So this is what's called Laplace's method, right? You can see at the core, we just have Taylor series, right, for constituent functions. We're just choosing them for the right functions so that we get this nice integral in terms of a Gaussian, which we can take. Okay, so I won't prove Laplace's method in detail, okay, but if we just want to get a sense of a sketch of a proof, I of x equals this integral from a to b, f of t, e to the x phi of t dt. The idea is that we're going to find the neighborhood of some max of phi where the integrand and exponent can be expanded in some Taylor series, okay? In that case, we can write I of x to leading order as c minus epsilon, c plus epsilon, f of t, e to the x phi of t dt, right? But to go further, right? So if we make our change of variables, t equals some function t of s, such that phi of c plus t of s is equal to minus s squared, as long as phi prime prime of c is less than 0. So take that specific case, then I of x is going to be given by an integral from values I'll call alpha minus and alpha plus e to the minus x s squared f of c plus t of s t prime of s. We're just going to show essentially that we have the right leading order terms in this case. Alpha plus or minus is equal to minus phi of c plus or minus epsilon here, okay? And this integral really is now a generalization of that given in Watson's lemma, okay? And then we can use this generalization to obtain asymptotics, okay? Okay, so we're just basically showing that we can convert this integral to a form that looks like the integral we dealt with in the case of Watson's lemma. And then we're not going to go through all those steps that we went through last time in terms of Watson's lemma, but you could essentially follow through a very similar procedure and be able to show that to leading order, the things that we've retained are the primary contributions to that integral. Okay. All right. So all this is to say, this works well, as long as you have a Laplace integral that meets these conditions. There's obviously some caveats, like, when things are 0, you need to go to next order up, okay? And so it helps to go through a few examples. So let's look at maybe a couple of examples right now just to demonstrate. Okay, so we still have a good bit of time. So if, for example, we have the integral I of x is equal to the integral from 1 to 2 of e to the x cosh t dt, as x goes to positive infinity. Okay, I'm going to expand cosh, right, around its maximum. So what's hyperbolic cosine look like in this case? Well, it's going to look, pretty exponential, right? So our maximum is right here. It's on the right-hand side, okay? So the leading order, I just get cosh of 2 plus, to next order up, we get sinh of 2 times t minus 2 plus so on and so on, okay? F is just 1, no matter what, okay? So our integral is going to be 2 minus epsilon up to 2 e to the x hyperbolic cosine of 2 plus hyperbolic sine of 2 t minus 2 dt. Okay, this is equal to e to the x hyperbolic cosine of 2, and then just to be precise, this should be, technically this is the leading order. This is going to be the integral to from minus infinity up to 2 e to the x hyperbolic sine of 2 times t minus 2 dt. Okay, so this is equal to e to the x cosh 2 divided by x sinh of 2, right, because it's just an exponential, e to the x sinh 2 t minus 2 evaluated between t equals minus infinity up to 2. And then I can write this as e to the x cosh 2 divided by x sinh of 2. Okay. So in the case of these right and left boundaries, right, rather than having to perform the Gaussian integral, right, I just have an exponential integral. And so the leading order term basically picks up this this factor that's scaling my t term here. But the exponential itself is just going to be 1 typically, because I'm evaluating it at the point that I'm expanding around, right? So this term here is just going to be 0, and then out at minus infinity, I don't pick up any contribution there. Okay, so that's like a case 3 example for this integral. Okay, let's look at another one. Let's say the integral from 0 to 1 of sine of t now, e to the minus x sinh to the 4th t dt as x goes to positive infinity. Okay. Now, the max of phi of t in this case is going to be at t equals 0. But of course, there's an issue here because sine of t equals 0 there. Okay. So f of 0 equals 0. Okay. And sine of t, it scales to leading order like t around t equals 0. Okay. So what we're going to do then is we're going to go up to next order in f of t. We're going to cut down to just a region between 0 and epsilon around the left boundary of the integrand. We're just going to retain t rather than sine of t now. And we have e to the minus x t to the fourth dt, right? So because the value here, right, at t equals 0 is going to be 0, but if we Taylor expand, then the next term we're going to pick up is just a
Is that sine to the fourth or sinh to the fourth in the exponent?
it's sinh to the fourth in this case.
Okay.
Yeah. Yeah. So we have to go out to fourth order in this case in order to get our sort of leading order term in this exponential. Okay. The next thing we can do though is we can expand our integral out to positive infinity. So we get e to the minus x t to the fourth dt. This holds for x large. If I let s equal x t to the fourth, then what I get in this case is a integral 1 over 4x to the 1/2 integral from 0 up to infinity s to the minus 1/2 e to the minus s ds. If I integrate this up now, I get 1 over 4, the square root of pi over x in this case, as x goes to positive infinity. Okay. So as long as this this expansion of f in this case goes to 0 algebraically as x goes to infinity, okay, we can always expand out to whatever the first non-zero term is in our f function in this case. Okay, because remember it's always going to be multiplied against an exponential that's going to fall off much more rapidly than any algebraically increasing function. And the advantage of having a Laplace integral in this case is that this is going to be some algebraic function if we perform some sort of Taylor series, and we can always integrate by parts our way out of this particular form of some power function multiplied by an exponential here. Okay, so a remark, just as long as f of t goes to 0 algebraically, okay, as t goes to a, c, b, right? Laplace's method will work, and otherwise the integral can be computed. Okay. So that's another example. Okay. Let's see if I want to try and do one more. example. Yeah, okay, let's try one more before we finish for the day. Let's say that we have the integral from 0 to infinity of e to the minus 1 over t minus xt dt as x goes to positive infinity, okay? And I can write this and split it up a bit as e to the minus 1 over t, e to the minus xt dt, okay? Now note, there's an issue here, which is that in the limit as t goes to 0 from above, e to the minus 1 over t equals 0, and e to the minus 1 over t has no Taylor expansion, okay? Around t equals 0, right? Because e to the minus 1 over t and its derivatives all are going to go to 0 exponentially fast, okay? Now, how do we deal with this integral in this case, right? Because this would be our f, right? But it's going to 0, and I can't really properly expand around it, okay? So the trick here is to consider the integral from 0 to infinity of e to phi xt dt. And what we're going to do is we're going to find the maximum of phi. So we're going to lump in this additional term, right, with our phi of x here, right? So it's not quite the form, our sort of standard form of Laplace integral. But note that if we take the derivative with respect to t, we get 1 over t squared minus x is equal to 0. So our t max now is equal to some value of c, right? And that's going to be 1 over square root of x, okay? Now, we have what's called a moving maximum, okay? No longer have a stationary maximum, so we need to treat our max somehow so that no matter what x is, right, we're always expanding about the maximum, okay? That's the issue that we'd run into if we sort of split it up, okay? So in order to transform the moving max to a stationary maximum, S is equal to the square root of t x. dt is equal to ds over the square root of x. This is going to give us now I of x is equal to 1 over the square root of x, integral from 0 to infinity, e to the minus square root of x, s plus 1 over s, ds, x goes to positive infinity, okay? So in general, right, we could try some s equals t x to the m, okay? And choose m, so this works, right? But notice that now, okay, some function of x, right, has been factored out of this function here, right? So we have some function that commonly multiplies whatever our power function of x is now, okay? So if I say, well, minus phi of s is equal to s plus 1 over s now, then minus phi prime of s is equal to 1 minus 1 over s squared. okay? And this is going to equal 0 when s is equal to plus or minus 1, okay? And phi prime prime of s is going to be equal to minus 2 over s cubed. And in particular, we'll evaluate this at s equals plus 1 to get minus 2, which is less than 0, okay? Because we're only dealing with the integral from 0 to infinity, so we only want to take the positive values of s in this case, okay? So now we have a function of s, right, which we can expand to second order, okay? We have a stationary max, and it's just that our x term now is just square root of x rather than x, okay? But we can still apply the same sort of stationary max Laplace method idea. And this holds for p equals 0, okay, where we just approximate our function phi of s to s squared. And if we do that, then we get a 1 over square root of x term out front. The same type of term that we typically get from Laplace method, right, which is going to be the square root of 2 pi over minus now square root of x rather than just x, phi prime prime of 1, e to the square root of x, phi of 1, okay? Or if we simplify this down, we get square root of pi e x to the minus 3/4 e to the minus 2 square root of x, okay, as x goes to positive, okay? All right, so that's how to handle those moving maxima, is to make these change of variables and figure out how to factor out this term of x so that you have something that is of a stationary max form for Laplace's method, okay? So just to sum up, okay, Laplace's method, what's the idea? The idea is that you have some function that's scaling, okay, x in your exponent, and that is going to have a sharp max that really is going to be the primary leading order contribution to your integral. You want to Taylor expand phi around that stationary maximum, okay? And then you can, extend the limits of integration so that you can integrate. And in that case, your prefactor, your f, right? It just matters what its leading order contribution is there in that case. And by virtue of the fact that Gaussian integrals can be computed analytically, you have a handy form in order to give you an explicit expression. And depending on whether you're, on the left or right boundary, that just may be a simple exponential integral, okay? And as we just saw, if we have a moving max, you need to perform some sort of change of variables. So really the key tools here are change of variables as well as Taylor expansion, right, which we've used a lot in our other asymptotic methods, okay? But this is a much more reliable method than integration by parts, as long as you have a Laplace form integral. Okay, that's all I've got for today. Are there any questions before we wrap up? Okay. Okay, so I think on Wednesday, we're just really going to do maybe a little bit more on this moving max idea. As I said, if you want to look at higher order expansions, all those readings are referenced on the calendar. I would encourage you, especially as you're doing the homework, refer to the book. I can't cover every single thing there is to know about these asymptotic methods, but Bender and Orszag is pretty exhaustive. So familiarize yourself with that book. And yeah, so on Wednesday, we'll sort of wrap this up and move on to stationary phase. And yeah, it won't be long till we're talking about matched expansions for differential equations. So probably just another week on integrals before we move on to ODEs. Okay. Thanks, everybody, and see you on Wednesday, if not before.
Thank you.
Thanks, Zach.
Thanks.